Welcome to the Explainer. Have you ever stopped to think about what a planet orbiting the sun, a speeding bullet, and the phone in your hand all have in common? Well, it turns out they all follow the exact same rulebook, a set of rules written over 300 years ago that literally dictates how everything in the universe moves. Today, we're going to decode them.
So here's our game plan. First step, we're going to meet the absolute genius who cracked this code of motion. Then we'll break down each of his three huge world-changing laws, one by one. And then, and this is the really important part, we'll connect it all back to you and show you how these old-school principles are actually at work saving your life today.
You know, the answer to that question isn't found in some high-tech modern lab. Nope, it's in the mind of one person from way back who basically wrote the instruction manual for the entire universe. Okay, let's get into it. Section 1, the rules of motion. This is the man himself, Sir Isaac Newton. Now, he wasn't just trying to solve some homework problem. He was on a massive quest to find one single beautiful system that could explain both why an apple falls from a tree and why the planets stay in their orbits. So picture this. The year is 1687. Newton drops his masterpiece, the Principia Mathematica. And this isn't just another book, it's a total game changer. In these pages, he completely rewrote how we see the entire cosmos, forever. All right, let's dive into his first law. This one is all about something called inertia. And you can think of it as a kind of fundamental laziness that's built into the universe. It's a resistance to change that you feel every single time you're in a car that speeds up or slams on the brakes. The main idea here is actually really simple. Things just want to keep doing what they're already doing. If they're sitting still, they want to stay still. If they're moving, they want to keep moving at that same speed in that same direction. The only thing that can possibly change that is some kind of outside push or pull, an unbalanced force. Just think of a running back in football, right? He is blasting down the field. He's got all this momentum. His inertia, that tendency to just keep on going, is what that defender has to overcome. It takes a massive, unbalanced force to actually stop him. And this whole inertia thing works on a cosmic scale too. Out in the vacuum of space, where there's pretty much nothing to slow it down, a satellite's inertia will just let it coast forever. No engine needed. It just keeps on going.
Okay, so we know an unbalanced force changes motion. But how much does it change it? That is where the second law comes in. It gives us a super precise mathematical way to figure that out.
So, in plain English, this law is really telling us two things. First, the harder you push on something, the faster it's going to speed up or accelerate. Makes sense. And second, if you use that exact same push, heavier things will accelerate a lot less than lighter things. And believe it or not, that entire relationship is summed up in this one beautiful, iconic equation. F equals ma. Force equals mass times acceleration. Just 3 letters that define one of the most important rules in all of physics. I mean, it's pretty intuitive, right? You know from experience it's going to take a whole lot more effort to get a car rolling than it does to push a shopping cart. If you want them both to accelerate at the same rate, the car, with its much bigger mass, is going to need a much, much bigger force. So we've got that forces cause acceleration. But Newton's third law tells us something even deeper about forces themselves. They never, ever work alone. Every single force in the universe is actually part of a pair. Put simply, anytime you push on something, that something is pushing back on you with the exact same strength. No, really, it's happening right now. As you sit there, your body is pushing down on your chair, and that chair is pushing right back up on you with an equal and opposite force. You can see this in the most powerful way you can imagine with a rocket launch. The action is the engine blasting hot gas down towards the ground. The reaction is all that gas pushing back up on the rocket with the same force, sending it flying into space. And this explains a much more common thing, too. You know when you jump from a little boat onto a dock? Your legs push backwards on the boat. That's the action. And the boat, in turn, pushes forward on you. That's the reaction that sends you flying to the dock, while the boat itself shoots backwards. Okay, so why should you care about a bunch of laws from over 300 years ago? Well, because understanding just that first one, the law of inertia, is absolutely essential to understanding your own safety in our modern world. Think about your brain for a second. It's actually a lot like the liquid yolk inside this raw egg.
It's a soft tissue that can kind of float around and move independently inside the hard shell of your skull. So when you stop the eggshell, see how the liquid inside just keeps on spinning? That's its inertia.
Now, imagine that in a car crash. Your skull might come to a very sudden stop when it hits something. But your brain, oh no, your brain is still obeying Newton's first law. It keeps moving forward because of inertia, and it slams into the inside of your skull. And that right there, that collision, is exactly how concussions and really serious brain injuries can happen.
So, Newton's first law isn't just some dusty old concept from a textbook. It's the fundamental reason we have all these life-saving technologies: seatbelts, airbags, helmets. Every single one is designed to safely manage your body's inertia when everything comes to a sudden, violent stop. For hundreds of years, these laws were the perfect tool for predicting motion, but they also led us to a much deeper, much weirder question about the universe itself, a question that would take us from the incredible mind of Isaac Newton to the truly mind-bending realities of Albert Einstein.